We're going to be introducing Big Idea 2 in the next 3 chapters that we talk about. We're going to be reviewing the periodic table, periodic trends, taking it to a whole new level. Chapter after that, we will be reviewing how to draw compounds, getting into some compounds with expanded octets. Then we'll get into the different shapes. For example, bent, linear. We'll talk about some newer shapes like seesaw, as well as trigonal bipyramidal. And then finally, we'll talk about intermolecular forces that exist between molecules. So Big Idea 2, you want to be able to demonstrate that chemical and physical properties of materials can be explained by the structure and the arrangement of atoms, ions, or molecules and the forces between them. Before we can get into that in great depth, we need to talk a little bit about atomic structure first. So this is chapter 7 in your notes. There's a little bit from chapter 2 in your textbook. A lot of this is review. We'll go through the theory relatively quickly. You've seen it all before, and we can show a lot of it just with a few little video clips, and then we'll get into electrons, waves, lights, relationships between variables, etc. So with atomic structure, back in 1803, John Dalton talked about the first atomic theory, where he said the atom is spherical, it's indivisible, and indestructible. Soon after that theory came out, experiments by Faraday, Crookes, and especially J.J. Thomson showed that the atom is in fact divisible because subatomic particles such as the electron, proton, and neutron existed. Thomson is credited with the discovery of the electron and the proton. And what he did is shown in the following video. A lot of it is written out here just so you have it. But what we're going to look at here, so this is a cathode ray tube. What you're going to have here is a cathode, a metal electrode, and an anode, also a metal electrode of a different charge. And you're going to hook it up to a voltage source. You're going to flip it on and look what happens.
It's a glass tube in which most of the atoms are vacuum. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light.
Now they're going to apply an electric field. Why might you apply an electric field? What do you want to determine? The charge.
When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges.
The fact that it is attracted toward this plate with a positive charge suggests that this beam is comprised of what kind of charged particles? You got it. Better known as electrons. So cathode rays are electrons.
Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1997, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode.
Now clearly too much information, but what you want to know is that Thomson was able to calculate the charge to mass ratio, and we'll show the importance of that. The theta E and all that other stuff, too much.
Thomson determined the charge to mass ratio of an electron to be negative 1.76
coulombs. And we're going to get into coulombs later in the year. You're not going to see it at this point. At this point, you want to know the electron is negative and the proton is positive. They have equal but opposite charges. If you actually consider the quantity per se, you'll see it's 1.6 times 10 to the negative 19 coulombs. And that quantity, that constant is given to you on your formula sheet. So it's not something you have to memorize, but we're not going to get into it.
Coulomb's a unit of
Charge.
What's the abbreviation for coulomb?
Capital C. And you're actually going to see it on your formula sheet, which is on the back of your periodic table. There are two formulas given for atomic structure. They should be familiar to you. We'll be reviewing them today. And you'll see the direct relationship between energy and frequency and the inverse relationship between frequency and wavelength. Those constants are given, so electron charge, that quantity is given to you. Alrighty. So, at this point, in regard to Thomson, he was able to show that cathode rays are negatively charged particles, and we saw that in the video. Doesn't matter what gas is used, the deflections are the same. So cathode rays are not ions, but rather charged particles that are found in all matter. And as I said, he was able to determine the mass to charge ratio, which is shown here. Most importantly, that value that he found for the mass to charge ratio of those cathode rays is about 2,000 times smaller than what's known for a proton. That suggested a smaller entity than a proton, and that is a subatomic particle. So the electron is much smaller than proton for mass to charge ratio. Now the person who actually coined the term electron is George Stoney. Interesting, but not something you need to know. J.J. Thomson, with cathode ray tubes, discovered the electron. He also was able to calculate a mass to charge ratio. To calculate the mass of an electron, this was work done by Robert Millikan in 1909. And this is his oil drop experiment, and this explains it pretty well.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the
This
droplet.
is kind of cool. Watch this.
When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19 coulombs. He took them to be the charge on a single electron.
So Millikan was able to establish the charge on an electron and in turn the mass of an electron. And we know the electron is the smallest of the three subatomic particles. This led to additional models for the atom, which I will outline here. So from J.J. Thomson's findings, Lord Kelvin, along with J.J. Thomson, came up with what's known as the plum pudding model. And again, you saw this in honors. And this model says the atom is spherical, there is a sea of positively charged particles. Those are the protons. They knew that positive charged particles had to exist because the atom is electrically neutral. So for every negative, you had to have a positive. And then in the sea of positive charge, which essentially would be the pudding, think about vanilla pudding, you would have these little raisins, which are the electrons. So you'd have raisins or little plums, etc. And this became known as the plum pudding model. J.J. Thomson and Lord Kelvin. Rutherford tested this model. And the way that he did that was that he had a piece of gold foil. I'll establish it for you first. I don't have an image in here. I can add any images that you think you need. Hang on a sec. Let me set this up for you. Here's your gold foil. So you have atoms of gold. Here is your alpha particle emitter. It's going to shoot positively charged species at the gold. And you're going to see where that beam goes. You would think that if it hit a whole area of positive charge, that most of those alpha particles would be deflected because the atom would block its path. Yet watch what happened.
Workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected.
And it really does go fast. So most of the particles went straight through as if you were at the range shooting a gun at a paper target. Most of them just go right through the paper target because there's nothing to block its path. However, a few of the particles were slightly deflected, and some of them had great deflections. Watch the green screen now.
However, a few were
Right
found
there.
scattered at large angles.
Right there. Right
Right
there.
This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electron. The nucleus is small and massive. When an alpha particle
So most of these particles go straight through because it's as if they hit empty space. Most of the atom is just empty space.
What charge is that particle?
You tell me.
Yeah, I guess positive.
It is positive. And do you remember from last year what an alpha particle is?
It's like
H.
the H and then
E.
oh,
It's a helium nucleus. Remember, you had the 4, the 2, and the He? It's a helium nucleus. And so it is positively charged. So most of it goes straight through, but if it hits this dense nuclear core region, that's when you get the deflection pattern.
encounters a nucleus, it is scattered at a large angle.
And for those of you who are interested, those DeWitt videos are very good, although the ones that I really think are the best are the Bozeman videos that I recommend you watch. Those recommended videos are in your course outline. So Rutherford's experiment, and again, alpha particles are positively charged particles, go right through the foil. Some are deflected, and a few even came straight back. And that meant that there was a very small nucleus that contains almost the entire mass. So most of the mass of the atom is due to the nucleus, where you have positive charge. When you look at the mass of an atom, it is greater than the mass of a proton alone. And that suggested that there had to be another subatomic particle. In 1932, James Chadwick discovered this other subatomic particle that was shown to be neutral. And let's take a look at that one.
Your binary meeting is family of 8 over a home-cooked meal big enough for 30. When
Discovery of neutrons. According to Rutherford, the nucleus of an atom contained only protons, and these protons
Now this is what he believed prior to his experiment. So this is what the plum pudding model showed.
decided the mass of an atom. But we know that hydrogen has 1 proton in its nucleus, whereas helium has 2 protons. If the protons were the only particles in the nucleus, then a helium nucleus would have 2 protons and therefore only twice the mass of hydrogen. However, it actually has 4 times the mass of hydrogen. This suggests that there is some other type of neutral particle present inside the nucleus along with the protons. This mystery was put to rest when James Chadwick discovered neutrons in 1932. Let us now understand the experiment performed by Chadwick with the help of a flowchart. He placed a source of polonium in an evacuated chamber. In front of the polonium source, a thin foil of beryllium was placed. The alpha rays were made to hit the foil of beryllium. The beryllium foil emitted the mysterious neutral rays. Chadwick placed a target in the path of these rays. These rays knocked out atoms from the target. These atoms, which had become charged as a result of collisions, were made to enter a chamber filled with gas. These charged particles ionized the gas, and the ions drifted towards an electrode, constituting a current. By measuring the current, he estimated the speed of the ejected atoms and came to the conclusion that the mysterious rays contain particles having mass almost equal to that of the protons. Chadwick identified these uncharged particles as neutrons.
And I just want to go back for a sec. This diagram was very misleading, and I think I misled you.
Discovery of neutrons. According to Rutherford, the nucleus of an atom.
So I'm sorry, I misunderstood what they were showing here. This is a blow up of the nucleus, and that wasn't clear to me initially. So prior to Rutherford's work, we had the plum pudding model, and then upon the gold foil experiment, this is the nucleus only. You're seeing the positive charge there. So I may have misled you there. I apologize. The diagram initially to me was misleading, but this is the nucleus only, not the atom. So it's a blow up of that dense nuclear core. So James Chadwick, and he actually had quite a bit of help from Irene Curie, but she didn't get much credit, and that unfortunately happened in science in the 1900s. You saw it with Rosalind Franklin as well with the discovery of DNA helix. But Chadwick is credited with the discovery of the neutron. So J.J. Thomson, electron and proton, Chadwick, the discovery of the neutron. What will be new to you is mass spectrometry. And this is a very complicated process. I'm going to try and really simplify it for you. A mass spectrometer looks something like this. And I have a Pogo packet for you. I know with your quiz on Monday, you're not going to look at this, but I would like you to look at it Monday night. Let me hand it out to you so you have it in front of you. But a mass spectrometer is used to determine the mass of atoms. And it's especially helpful when you have isotopes. And I'll show you briefly how it works. This is actually in a previous chapter in your notes. It's right at the beginning, in your textbook rather. It's right at the beginning of chapter 3. I did go into it then, and I didn't really feel like it belonged. You better clean up that mess. Right over. Make sure you clean up that mess.
Are subatomic particles unbreakable?
No, what he's saying are subatomic particles indestructible. I think they are. I think they are indestructible.
What?
All right, so this is your POGL packet on mass spectrometry, and I like this one. Let's take a look. So what you're looking at is right here. You have a mixture of isotopes, in this case magnesium, and you put it into the mass spectrometer. And then it goes through an ionization process. We'll look at that in a minute. And you're going to generate magnesium ions. You're going to accelerate it through a field, and you're going to look at its deflection pattern. And you will find that lighter ions deflect more than heavier ones. So the greater the mass, the less the deflection. Think about it. If you go to the beach and it's very windy and you try and throw a beach ball around, which is very light, it's going to blow all over the place. The basketball's not really going to be affected very much. And you can see that here. So whatever sample, you're going to vaporize the sample. Here's your beam. You're going to generate ions, and they're going to move through this field. They're going to be accelerated. The most massive ions will be here. The less massive ions will be here. They'll be deflected far more. And what's going to happen here is you can compare where these ions hit the detector, and that is related to their masses. And what you're going to generate is a mass spectrogram. And we want to take a look at that and try and analyze that a little bit. This is a newer edition of your textbook. It just has some good questions in it, but you have similar diagrams, identical diagrams in your textbook. So for example, if we are to look in your textbook, and I didn't have any clips in here other than what was in the book, so I didn't insert it. For example, here's neon. You can see neon gas glowing in discharge tubes. You would see that, for example, and maybe at the bowling alley, it'll say open, a neon sign, or at the pizza place or something. Shown in B are the peaks, that is the ion beam intensity at the detector with their corresponding mass numbers. So you know neon has a weighted average atomic mass of about 20.18 AMU. And if you consider that here, you'll see that you have the greatest ion beam intensity at the detector with a mass of about 20, but you do have some other isotopes here, just not as abundant, with mass numbers of 21 and 22. What you more commonly would see is the bar graph shown here, and what you're looking at is the relative number of atoms versus the mass number. And you can see that neon 20 is the most abundant with a percent abundance of about 91, and the least abundant of the isotopes is neon 21 with a percent abundance of only about 0.3. So given the percent abundances and the masses, you could determine the weighted average atomic mass. Perhaps easier to see is this one here for copper. How many isotopes of copper do you have? 2. These are their mass numbers. Which is more abundant? Copper 63 with a percent of 69.09. And we talked about how to calculate weighted average atomic mass earlier, so you could calculate it from the graph. What I also want to show you is 2 multiple choice questions that were in practice quiz 1-3. I told you to skip them at the time, but now we can go back and take a look. The second one's actually easier than the first, so I'm going to do the easier one first. It says an unnamed element with an atomic number of 130 is vaporized and injected into a mass spec. The results are shown below. Use these data to calculate the average atomic mass of this element. So we've got how many isotopes? 2. Which is more abundant? 320. Now, before you try and answer the question, if you had 50% of each of these isotopes, what would the average weighted atomic mass be? 322 is correct. But you have 75% of 320 and 25% of 324. So, what would the average weighted atomic mass be without a calculator? 321 is correct. And you just look and you've got it. All right? No calculator required. We didn't even write anything down because you have more of this one than this. So if it was 50-50, it'd be in the middle. So it's got to be closer to this than this. And it's not 320 or you would just have that one. So just, and we're going to do a lot of math without a calculator today. You've got to get comfortable with this. I know a lot of you are sick and you really should not be in school. Do your best to focus. All right? It's very tough when you don't feel well. I recognize that. Here's the first question. This one's a little trickier. You'd be more apt to see the second. It says, when a sample of an unknown element is vaporized and injected into a mass spec, the results shown below are obtained. Use these data to estimate the average atomic mass of this element. Well, we've got a whole smorgasbord of isotopes. You can see the highest peak is at 120, but there's a pretty good sized peak at 118. Would you guess the mass number to be 117? Probably not. Between 117 and 118? Getting closer. Between 118 and 119? Probably. Between 119 and 120? Close but no cigar. I agree with you. The answer is C. Alrighty? That's a little tough because there's so much going on. The second question's much more manageable. These two questions are in Practice Quiz 1.3. You may want to scribble that down in your notes just so you've got it. So that's mass spec, and I've given you a POGIL packet that is more than you would ever want to know on mass spec. But if you work through it, especially on those middle pages, they give you some of these line graphs, and you can do some of the analysis, and I think if you work through those few problems, you will be very, very comfortable with it. The extension questions you won't be able to do yet, but if by Tuesday you can work through pages 1 through 5, I think you will be in extremely good shape. Don't scribble through page 6. We'll get there eventually, but we're not there yet. And even with your knowledge from last year, you won't be able to do that with ease. So as I said, these questions, and I have in your notes, mass spec questions, APMC multiple choice. What this, it may be easier for you to see is APC PQ 1.3, and that would be part 3, questions 1 and 2. So that may help you gear yourself toward which questions you'd want to review. All right, the other thing we want to do very briefly today is review some aspects of light and waves. Electrons determine the chemistry of the atom, so it's very important to understand electron behavior. To understand electron behavior, if we understand the wave nature of light, it's a little bit easier because electrons have a lot of properties of waves and light. So light is made up of electromagnetic waves that propagate through space, and a wave, for example, if you have a jump rope and you're holding one end and somebody's holding the other end and you jerk it, you make waves. So it's a progressive repeating disturbance, and it'll spread through a medium from wherever you start to more distant points. Electromagnetic radiation is characterized by some common features. One is wavelength, one is frequency, one is amplitude. The wavelength, you should recall from both honors chemistry and math. So wavelength is abbreviated with a lambda. You better have a unit of meters or you are going to crash and burn. If, for example, you had a sine curve, it would look something like this. And your wavelength would be that distance. Do you remember this?
Yeah.
Okay. So wavelength. Couple conversions you better plant in the brain. 1 meter is equal to 10 to the 3rd millimeters, or 10 to the 6 micrometers, or 10 to the 9th nanometers. That's a sloppy 9.
Can't see it.
Oh, that's okay because I'm not sure it's all that visible. I'm going to write this one again.
What is the 10 to the 6?
That's micrometers, micrometers, and this is nanometers. You've got to know those conversions. Frequency, and this is all on your formula sheet, has this funny V, and this is going to be either in seconds to the -1 or hertz. They usually give you hertz, but seconds to the -1 is going to help with your unit cancellation. The amplitude is the height of the wave, and you may or may not remember that the speed of light, a constant, is equal to the wavelength times the frequency. Wavelength and frequency are inversely related. As one goes up, the other goes down. The speed of light is a constant. It's given at 2.998 times 10 to the 8th meters per, oopsie, that's just a mess. We'll make it neater. Meters per second. And that's why your wavelength has got to be in meters, otherwise it's not going to cancel. Now when you do these problems in your head, it's easier to just use this, and I'll show you how. So wavelength and frequency are inversely related. The first example is given. I'll walk through with you, and then I'll do the second one. In your notes it says times. I tried to put that little star in because some of the kids were confused with the X. It says calculate the frequency in hertz of a microwave that has a wavelength of 1.07 millimeters. First thing you want to do is convert millimeters to meters. Just divide it by 10 to the 3rd millimeters. I gave you this conversion. You've got to know it. Once you're in meters, it's a plug and chug situation. Here's your speed of light. Here's your wavelength. Solve. And without a calculator, let's review some basic math skills. 3 divided by 1 is obviously 3. 10 to the 8th divided by 10 to the -3rd. So you are subtracting when you divide. You have 8 minus -3 is 11. And when you get in the car, I don't know how you're going to do this, but when my daughter gets in the car, I hate the texting, I hate the iPod, I hate it all. So I take every little device and I throw it in the back seat, provided nobody's back there. And I make her do math games. And she hates it, but I love it. So I'm like, Sam, what's 3 minus 6? -3. What's -3 minus 5? She goes, 8. No, 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 you've got, -8. You've got to be very comfortable with this type of math. You've got to be able to do math without a calculator in AP Chem. I know you don't like it, but it really tastes much better than some of the medicine I'm sure you're taking for your sickness. All right?
I didn't see that logic.
There you go. It's fun. Math is fun. It does taste better. All right, let's look at the example without the calculator. Let me show you how you can do this without a calculator. Here you go. It says calculate the wavelength and they want it in nanometers, of visible light that has a frequency of 5.0 times 10 to the 14 hertz.
The lambda looks like a plus sign in Google Docs.
Oh well.
It doesn't convert at all. That's really funny.
Alrighty, we know that the speed of light is equal to the wavelength times the frequency. If we're solving for wavelength, we're going to divide both sides by the frequency. If you can't manipulate variables, Houston, you got it. Now, without a calculator, we're going to use 3 times 10 to the 8th meters per second. And we're going to divide that by 5 times 10 to the 14 hertz. Now, hertz is seconds to the -1, probably easier to use. This will cancel. And now, 3/5 is 0.6, right?
Yeah.
So we have 0.60 times 10 to the 8 minus 14 is? See, those math games. Now, 2 problems. You don't write scientific notation like that, and the question called for nanometers. I'm running out of space, so I'm going to swing here. 0.6 is the same as 6.0 times 10 to the -1, correct?
Yeah.
Yes? Yes? Times 10 to the -6, and that's 6.0 times 10 to the -7 meters. Now you want to go to nanometers. 1 meter is 1 times 10 to the 9th nanometers. And that's going to be equal to -7 plus 9 is? 2 is correct. Final answer. Lock it in.
That's not that big.
It's not so bad, but you've just got to be systematic with it. All right? When you do your practice quiz, which I won't give you till Monday, well, you're going after 2 sig figs, so be careful because 600 would only have 1 or 3. When you do your practice quiz, the multiple choice questions, bury that calculator. All righty?
We have a funeral?
No. Last thing I want to mention for today is where visible light falls on the entire electromagnetic spectrum. So visible light on the entire magnetic spectrum is just a very, very, very small region. So, you're looking only here at Roy G. Biv, the same rainbow you would see in the sky after it rains. We've got radio waves. That's what you're listening to half the day. We've got microwaves. For some of you, that's how you cook all your food. If you really want to giggle a little bit, go watch Worst Cooks on the Food Network. These people don't know how to make anything. And for those of you who need a little afternoon laughter because you're so stressed over school, highly recommend it. Infrared radiation, visible light, UV radiation, that's what you're exposed to by the sun. X-rays, break your arm, go to the dentist, etc. X-rays, cosmic rays. No, I mean if you break your arm and you need an X-ray and you go to urgent care or the emergency room, or when you go to the dentist and they look for cavities, etc. You have no arms.
My dentist has a broken arm.
Your dentist has a broken arm. Super.
She did it like an if then class. She was like,
All right.
break your arm. Go to the
We're not in English class. As you go from left to right here, the energy increases big time. The wavelength decreases. The wavelength of a radio wave is about a football field. very, very long. Gamma rays wavelength, very, very small, very high energy. We'll talk more about the energy relationship next time. If you look on the electromagnetic spectrum, here's visible light right here. It's very, very small region of the whole electromagnetic spectrum. And we'll pick up with the spectra in more detail next time. Your take-homes for today. Wavelength and frequency have an inverse relationship. Can you calculate both without a calculator? Do you understand the discovery of the subatomic particles and the role that the people played in it? But again, we're talking maybe Thomson, Rutherford. Those are the key players that you need to know. You also want to be comfortable with mass spectrometry and reading those spectra, and if you do that Pogel packet, you'll get a lot more practice and you'll feel very comfortable with it. Other than that, I think most of what we talked about is review. Next time, what we will get into, we'll make that Tuesday, will be line spectra. We'll take a look at it. We're going to look at the direct relationship between energy and frequency. There's a new component there this year that we'll talk about. We'll introduce Bohr's model, and finally the quantum mechanical model, and we'll start to review writing electron config. There's also a key component right here, and this video, it's not really a video, it's a modeling simulation. It's really cool. You get to see how the molecules dance, so you'll want to take a look at that if you're going to be out. And we'll start to review electron configuration without the subshell tree diagram. You have to be able to write electron config from the periodic table only. You'll be very successful with it. All right? So this is the very beginning of atomic structure fitting into big idea 2. Again, not too much new stuff today. We'll get into more new stuff on the next block day, and we'll transition now into the next piece. Okay?